All right, congratulations. You've completed the vector part of this course. So we're now starting into calculus. And this is now a completely different course. Right? You can think of this as going from one course to another. I mean, it's still math, but it's a completely different branch of mathematics. Very, very different ideas. Um, so the stuff that we had done before with all the vectors, that's gone. You won't be worrying about that again until the final exam rolls around. Calculus is now more of a course that's going to follow from the advanced functions course. The grade 11 university and the advanced functions all lead towards this, whereas the vectors sort of did dance around to different ideas a little bit, kind of like data management does, right? A little bit different than the other courses. So this should look a little bit more familiar. We're dealing more with functions and function notation and algebra, certainly all two-dimensional stuff, right? We don't have to do any 3D. There's still graphing, and we'll still have that. But from a trying to visualize it perspective, it's a little bit easier. Lots of people ask, is calculus harder or is vectors harder? And that's a tough one. Different people take it different ways. Some people, as I said, some people latch onto one more than the other. So it's hard to say. One of the tricky parts is, as we're starting up calculus, is just trying to get a hold of the ideas of what we're actually trying to do in the first place. And once you get that, then you're set. A lot of the units, use knowledge that we've used already to build on things. So once we get started, then we'll be off to the races. Calculus, primarily, at least as we're getting started, is all about the idea of trying to represent slopes. So we've got that blue line there, and it says, can you get the slope of the line? And of course, we can do that. You could have done that back in grade 9. Right? To get the slope, you need the rise and the run. So slope was rise over run. And in this case, we went down 2 and over 3. So we had a slope of minus 2 over 3. Right? We've seen that before, although probably not recently, I suppose. Can we determine the slope of the curve? That's the calculus problem. So is there a way, is it even worth something talking about? Is there such thing as the slope of a curve? And fundamentally, there isn't. Right? The slope of a line works because that minus 2 over 3 works everywhere on the line. On the curve, simply by the name, it curves, right? There isn't a consistency to it. So from one point to the next, the rate of change of this function is going to be different. For example, if I think of sort of that section right there, well, it's positive at least, right? It's on its way up. Whereas if I look at something down here, now we have a rate of change that's going down, it would be negative. So in different places on the graph, your rate of change could change from positive to negative. It could be a large number, small number. There's all kinds of things that will happen. What we're going to try and do with calculus is we're going to try and figure out ways of representing that rate of change. And that can only really be done, well, eventually at least I should say, with formulas, because it's going to change depending on where you are in the curve. So as we begin, today at least, we're just looking at sort of some ideas to get started. How does rate of change work graphically if I'm just looking at things? But gradually as we go, we're going to be looking at how we can make everything work with equations. So slope of a line, here's our easy one again. Determine the rate of a change by calculating its slope. So a little more formally than that warm up. Slope is rise over run. And what would it be on this one? Over 1 and up 3. So our slope is just 3. Okay, there's a line. And it says if the graph is a straight line, then the rate of change, and rate of change is just code word for slope, is constant. So for that line, no matter where you are, the slope is always 3. And then we get a curve, and we'll start with a simple one. There's just a parabola. So at least it's something we're familiar with. The rate of change is going to be different now depending on where we are. So there's 2 different ways we can do it. There's something called an average rate of change. And sure, I'm assuming that you guys remember a little bit of this from the advanced functions course, so I don't want to dwell on it too much. But I don't want to I don't want to ignore it either and just skip right past this stuff. So an average rate of change is determining the rate of change between 2 points. And we do that by drawing in a secant line. So we pick 2 points on the graph and we draw it in. Okay, and this really is just graphically right now. Okay, I've drawn it and we can calculate the rate of change that way. The other way to do it is to calculate the instantaneous rate of change, and we do that by drawing a tangent line. Tangents are tricky. Secants aren't too bad, right? Because you just pick 2 points and draw a ruler through, draw a line with a ruler through it. A tangent, the idea is that we're touching that curve at exactly 1 point. Or I should be more careful there. We're touching that curve at exactly 1 point in the vicinity. Okay, so near to it, it's only touching in one spot. That's tricky to draw perfectly. So if you try and draw one of those, the chances of you drawing it perfectly are slim, but we do the best we can, right? Even if you look at mine there, it looks like the green line probably isn't even quite touching the red line, but we're drawing it so that it looks close. That's our tangent. So a secant goes through 2 points, a tangent touches at only 1 point in the vicinity. Now when I'm saying the vicinity, what I mean, and this is something that we probably don't have to worry about quite as much just yet. If we have a curve that looks, say like that, okay, and I want to draw a tangent line right here, my tangent line would look like this, more or less. And you can see right around this area, it only touches in one spot, right? But because I have a cubic this time, the graph keeps going. And in fact, we have a second hit. That's okay, we're not going to worry about that one. Okay, so when we write a tangent line down, we're saying it only touches in 1 point in a close proximity. So we'll try the example here. It's the same picture. Determine the average rate of change between x equals 1 and x equals 4. And that's what we see in the picture. So to do that, we would need our slope. And again, remember, this is just graphically. Everything we're doing today is graphical. We're going to worry about equations probably the next day or two. So for the rise on this one, move this out of the way. Rise on this one, we're going down 1, or excuse me, down 3 and over 3. So we're minus 3 over 3, or a rate of change or a slope of just -1. So an average rate of change can be calculated like that, just between 2 points. Oh, sorry, I meant to mention, I've short formed average rate of change to AROC, and then instantaneous rate of change is IROC. Just a lot easier than writing them all down, so feel free to do that. This one says determine the instantaneous rate of change at x equals 3. Now that's a tricky one, because I used the word determine, and I'm thinking about it now, thinking determine probably isn't the right word yet. Estimate is probably the right word. Because we're guessing where that tangent should go, right? We're not, if we just draw it in, I don't think we can be that confident that it's perfect. Turns out it is, by the way, but we wouldn't have known that ahead of time. So we're going to estimate the instantaneous rate of change of that tangent line. All that you know for sure is the 1 point we're focusing on, because it says determine the instantaneous rate of change at x equals 3. Well, there's your 3. So I'm going to put that point right on it. So that's the only point that I know for sure. 3, 3 is definitely there. And then depending on how I've drawn the line, I mean, in this case, I think we can see it right here. I could grab that point there, for example. That appears to be right on a grid line. But maybe as I draw that tangent line, maybe it doesn't hit that nicely, and I have to approximate where that point is. So that would be where the estimating part comes in. But in this case, you can see from there to there, be minus 2 over 1. So your instantaneous rate of change there is minus 2. But you can probably imagine, say I changed the question, I said determine the instantaneous rate of change at x equals 4. So down here. Well, that parabola is steeper now. So we could try and draw a tangent line in again, estimate where that tangent line would be, and the instantaneous rate of change would be something lower than -2, right? I don't know what it would be, -3, -4, right? It's going to be steeper. So the rate of change is going a little bit quicker. That's the idea of what we're looking at today, the idea of using a secant and using a tangent to try and determine these average rate of changes and the instantaneous rate of changes. So what I want you to do before you get to the homework, this is what we normally do in class, is we do this investigation. It's called this, that's the way the ball bounces. So you should be able to find that. I've linked it for you. I can show you a little bit. Here it is here. This is the file. It's representing a ball that's being bounced, right? So we're just dropping a ball and measuring the height each time. The scale on the bottom is in time. So we haven't, it's not like we're throwing the ball and watching it bounce. We're measuring it according to time. So point A up there at the top, that's where everything's starting, and we're falling down and just bouncing up. So we get a shape that's actually really hard to make an equation for. And that's because if you notice sort of this point down here at the bottom, that's called a cusp. It's going to bounce and bounce straight up again for the most part. We don't get a smooth curve like we do up here, right? The ball's going to hit the floor and change direction right away. So that screws some things up a little bit, makes equations really difficult. What I want you to do is try calculating, first of all, some average rate of changes. So it says for the interval AB, so from the point A up here to the point B, whoa, I don't know what that was. Sorry about that noise. From A to B, calculate the average rate of change. And you can do that two ways. You can just draw the line in and try and look at the slope. You got to be really careful on this one. This is harder than the examples we did because the scale's weird, right? Well, the scale's not weird. The scale is bigger, right? We're going up to 220 at the top there. So you have to be much more careful as you're calculating the slope. Also notice on your x-axis, we're in decimals there, right? Just 0.2 to get to point C there. So you write down the two endpoints and calculate the average rate of change. You can do that if you want to. If you remember from grade 9, we can use that formula, slope equals y2 minus y1 over x2 minus x1. You could do it that way. Or honestly, you can just look at this, I think, and you'll be able to tell what your rise and your run are. Let me see, the question at the bottom there. Sorry, this is tricky because usually you guys would do this and ask me questions as you go in class, and it doesn't work quite as well this time. If you want, just stop, try this part, and then start the video up again. What do the values for the average rate of change tell you about the path? Well, two things in particular, one thing in particular, you're going to get positive and negative answers for the average rate of change, right? That'll be the big one. So a positive rate of change means the ball's going up. Negative rate of change means the ball's going down. The other part would be how large a number is it? And I'm thinking absolute value there, so I'm ignoring positives and negatives. If the number is large, then the ball is changing height quickly. If the number is small, then it's changing height more slowly. Okay, so again, hopefully you've finished that. And then you take a look at part B. Similar idea for part B, but now we're calculating an instantaneous rate of change. To do an instantaneous rate of change, you've got to put tangent lines on here. And notice I said, draw the tangent lines. Oh, I can highlight that. Look at that. Draw the tangent lines. So draw them in. This is where we're going to have to do some approximating, right? It's going to be a little trickier to get a perfect tangent line. Just do the best you can. Notice it also said put your curve of best fit in there. If you draw that in first, it's going to make it a little bit easier to do the tangent line or to approximate the tangent line. So when you draw the tangent, you're doing the best you can to try and get the slope. And that will be tricky. Okay, it will be tricky. When you're filling out that table, and again, hopefully you've paused it and you're checking back in here now after you've already tried this. When you get to point X is right at the bottom there, right? That's where I said that cusp was, that corner is. You can't do an instantaneous rate of change there because the curve isn't smooth anymore. You can't, if you look at it and think about how you might try and draw a curve, or excuse me, a tangent line, would you draw it like that? Or would you draw it like that? Or like that? Or there's all kinds of lines that you can draw through that point without ever touching the curve anywhere else. So if you have a curve like that or a corner like that, we actually can't do an instantaneous rate of change. So we just sort of say, look, this can't be done. Okay. And then what's the last one there? Average rate of change over the interval. And what I want you to try and do is, so between point C and point F, and then see if you can find another point somewhere in between point C and point F, so that if you drew a tangent line, the slope of the tangent would be the same as the slope of the secant. Okay, so you're going to find an average rate of change first between C and F, and then can you find another point anywhere on the graph, doesn't even have to be one that's labeled, but can you find another point somewhere else where the instantaneous rate of change, so the slope of the tangent, would actually give you the same answer. And that should be possible. Okay, so there's your worksheet. This is still part of the lesson. Okay, so this would have been our normal lesson for the day. And then there's a little bit of homework you can take on after that.